Thanks for having me. I'm really excited to be back here at MIT where I got my degree. Really excited to talk about one of my recent work on testing with concept activation vector. This work is done with awesome collaborators at Brain, Martin, who is in the audience, Justin, Carrie, James, Fernanda, and Rory. So my research agenda is about making machine learning models more understandable by humans. Humans, even if they don't have machine learning background. Why do I care? Because machine learning is such a powerful tool being used everywhere, potentially making potentially high-stake decisions, and we want to use it carefully and responsibly. And that means that we want to ensure our values, things that we care, such as fairness, is reflected, and our domain expert knowledge, like doctor's expertise, is appropriately reflected. You can improve interpretability in many stages in your machine learning as you apply machine learning. You can do something with your data first, even before building any models. You can build a model that has interpretability inherently embedded in it. But often case, you are given a model, perhaps highly engineered model by many years, by many engineers, and you still want to improve interpretability. So today's talk is about a method where you can still improve interpretability given a model without retraining or changing the model. So here's a high-level goal of this work, testing with Teacup. Testing with CAV. The goal is to have a network that's given to you, but you want quantitative explanation of how much a concept like gender or race was important for a classification in this network. There's one problem, though. This concept that you want to test wasn't part of the training process. It was not a prediction label. It was not one of the input feature. Can you still test this? So let me give you some concrete example. You have a network. You build a beautiful network that takes a picture of a human, and it says how doctor-ness this picture is. Let's go to probability of a doctor. And I want to know whether the gender concept played a role. Did it matter that this picture happened to have a woman in it? Did it increase or decrease probability of doctor? TCAV is something that gets attached to the model. It's like a little microscope and studies and probes the model and tells you in numbers how much this concept was important or not important. There are 3 steps in TCAV. I'm going to talk about 2 of them today. It's pretty simple idea. Our running example is going to be finding whether stripes concept is important for zebra class. So first, your question should be, or might be, that what do you mean by this concept? How do you learn this concept? We compact this idea of a concept into a vector, and we give it a name, which is concept activation vector. How do we learn this? You need a couple of ingredients. First is example of the concept. If gender is of your interest, and if you consider gender as a binary concept, I need you to point out some female images if you're training an image network, and male images. So there you go. You have your example concepts. If you're interested in concept of female, so the examples of concept would be the female pictures, and you have random images, something that is not a female. As long as the majority of those examples are not female, you're OK. So I have these pictures, and you have the trained network that you're interested in investigating. And let's say you have access to the internal tensors. So function f here takes n-dimensional image and pipe it through the network and outputs the activation in layer L that happens to have m-dimensional. So now what we do, we pipe in these images into the network, and for all these examples and the random images, so f of L of all these pictures, and we train a linear classifier. Then we take the vector orthogonal to that linear classifier. What that means is simply a direction from random images to this concept. There are lots of different ways to do this. In fact, lots of previous literature show that you can either find median or mean of each of the concept, or random versus concept, and subtract those two to receive this vector. This is one way to do it. Yes? Oh, this FL is the model of interest that we want to investigate. What happened to step? Yeah. What was step B? I'll fix this notation for you, just for, yeah, good point. Forget about B. Look, imagine D is a B, it's a mirror image. So we have CAV now. We have a vector that represents this concept. What do we do with this? How do we get this score, how important the concept was in this classifier, which we call Teacup score? It's a really simple idea. It's an idea called directional derivative. I didn't invent it. This is an idea that existed many, many years. The idea is that taking a derivative of your zebra-ness, probability of zebra, with respect to this vector we just learned that represents the concept, in this case, stripes. And intuitively speaking, what this means is if you move a tiny bit along this vector, how much would your score of zebra change? If it changes a lot, this concept is important. If it doesn't change, concept wasn't important. Now we can do this for many zebra pictures that you have. And then we define a score metric that was used for this framework, but you can define your own metric. It's a pretty simple metric which says among all your zebra pictures you had, x of xk, how many of them returned positive directional derivative? And what that means is the existence of the concept increased the probability of zebra. Now you can think about flipping this inequality and say, what if I want to measure absence of a concept? Did it increase or decrease the probability of a zebra? Sometimes useful in medical applications. So you can define your metric that would be applicable for your application. Salience map is another method that is typically applied for image-based network to understand which part of this image that the network might be looking at. And it looks like this. What this is, in parallel to Teacup directional derivative, is that instead of taking the vector derivative, you're taking the logit layer probability of zebra with respect to every single pixel of this particular picture. So if you have a 50 zebra, then you have 50 of these pictures. And you can view Teacup work as a generalization of this salience map. Instead of looking at individual pixel in this particular picture, you now look at a whole concept across images that belongs to this class, all the zebras. So I'll show you some results. The first part is sanity check experiment. We just want to make sure we have a case where we have a ground truth, and we want to make sure that we're not completely hallucinating ourselves. So when we have a ground truth, will it match? The setup looks like this. We took images of cab, cucumber, and zebra. Then I went and wrote the caption in English, CAB or cucumber, on the left bottom corner on the images. And I varied the noise of which this caption has. What I mean is if I say 30% noisy, then 30% of the time, instead of saying cab, which is the right caption, I said tiger. And I built 4 different training sets, varying the noise level. Sometimes I didn't give it any caption, just to encourage model to look at different things. What I mean by look at different things? How does this help? Well, because I'm giving 2 signals to the model, it has a choice. It can either look at the image, pictures of a cab, and classify this as a cab, or it can look at the caption only and classify and use classification using the caption only. So there's 2 concepts of interest here, caption concept and image concept. How do I know ground truth? Well, we have, again, 2 models trained on 4 models, 4 different training data sets. If I have a model when I didn't give any captions, and I gave a test image without a caption, then it knows what to do. It's been trained on the images. It will look at the image, and it will say cap, or some other correct class. All these models has pretty high performance. when I give a caption with 100% accuracy, 0% noise, then it might choose to use the caption. In which case, when I give this test image without a caption, it wouldn't know what to do. Where's my caption? And it would achieve pretty low test accuracy. And that could be our proxy for ground truth, the importance of the image concept. So here's the results for two classes. For CAB, accuracy, the ground truth graph we just looked at in the previous slide, is a blue curve. Teacup score for the image concept is the green curve. And see, they nicely align. Story is slightly different in different class, cucumber class. And interestingly, CAB, all models across, whether we gave it 0% noisy caption or no caption, it always looked at the image. We had some hypotheses, but. So we talked about the Salience Map earlier. And you might wonder, well, can this map also give you the same information? Maybe. So let's look at it. So this is a CAB class. I'm showing you 4 different Salience Map methods, different types of method to generate this map. And I gave it a test image with a caption. So again, the ground truth is that CAB never looked at the caption. It always looked at the image. But when you look at the Salience Map, we see a little bit of glimpse of bright parts in the Salience Map. So when I look at it as a human, I might think, well, was it the caption important? I'm not sure. So to really verify this, we ran a Turker study. We showed Turkers, 50 Turkers, many, many pictures of zebra, cap, and cucumber alongside with their own Salience Map, and asked them, which concept do you think was more important, caption or the image? And we also asked them how confident they are. And results are really interesting. So first of all, I'm showing you one of the results for smooth graph, one type of Salience Map method for 2 models. And look at the right-hand side. This is a model where the caption had 100% noise. Turkers are split in half. They can't decide. Half of them say, oh, maybe caption, and half of them said maybe image. In the case, in 0% noisy case, Turkers did agree on one thing, except that one thing was the incorrect thing. They all thought, oh, it's a caption for sure. On the bottom, I'm contrasting with TCAV, where it nicely aligns with the ground truth, which was that image concept was important. What was more inspiring and alarming was that people were super confident. When they're answering these questions, this is how the very confident, it's the highest confidence they can mark in the survey. When they're correct and incorrect, they're equally confident. 40% of the time, they're very, very sure. And this might sound really familiar to people perhaps from psychology or HCI. This is a confirmation bias, a well-known effect that humans have. When you're given facts or evidence, you're very happy to pick out the things that agrees with your view. And this is not to say that Salience Map isn't useful. It's to say, well, when we give this explanation method to humans, we want to be very careful, especially when there's high-stake decision involved. So we were encouraged, and we ran this Teacup method on 2 of the widely used image classification network, Inception v3 and GoogleNet. Here's some results. We tested variety sets of concepts. We tested color concept, race, and gender. Now, when you look at the fire engine, the red comes out high, and green also comes out high, and the hypothesis there is that a lot of fire engines were sitting on the grassy field. Now, this would make sense, but do we have anyone from Australia in the audience? Yes, I heard that there's some yellow fire trucks in Australia. It's some part of Australia, they have yellow fire trucks, and this has to do with apparently humans are more alert in yellow than red in contrast to intuition. So this data set is actually showing some geographical bias. There are other results that confirmed previously qualitative findings like these ones, that African or Caucasian race high relevant to rugby ball, ping pong, Asian. And when I show this, not many people know why Asians are highlighted. Do you know why Asian? Yeah, right? Yes, thank you. Thank you. Yeah, I'm from Korea, and I'm really proud to say we win a lot of gold medals in table tennis. And I show this, and then some people were like, I don't understand. I was like, what do you mean you don't understand? Yeah, thank you. Thank you, yeah. So it's confirming that bias in the training set. And I have another graph that I'm not showing you here that shows that arms were important in dumbbells. And if you remember the very first Deep Dream blog post, they piped in, they activated one of the neurons for dumbbell, and they found this like muscular arms popping out in this Deep Dream. And they made a conjecture that maybe muscular arm is important for classifying dumbbell. And we show quantitatively here that, yep, arms were important in dumbbells. More details in the paper. So then now we took this method in the real world application, medical application. So diabetic retinopathy is treatable if you find early, sight-threatening if you left it untreated. So a team had made a very accurate model to predict DR level, one from very mild to 4 to very severe. And this model can predict DR level pretty accurately, 85%. The question that we have is, the concepts that machine learning model, this accurate machine learning model is using, is it consistent or inconsistent with diagnostic concepts that human doctors would have used? So we went and asked a doctor, what are the concepts that you use when you're diagnosing these two classes? DR level 4, she said, I look for these 3 concepts, and I look for absence of this concept, and differently for different level. So then we asked to Teacup, well, what do you think? For class DR level 4, which is the most severe level of DR, it was good. The model was using the concepts that doctors agree with. So these green bars are the ones that doctors expect to see high. The red, you don't want to see it, and it's low, so it's all good. Story was a little bit different when the model had medium accuracy. So for this level, DR level 1, which is the mild level of DR, it turns out that model has high score for this particular picture that doctors usually don't expect to see in level 1. This is type of hemorrhage. It's like a blown up vessel in your retina image. We wonder why, and we confirmed that the class that DR level 1 is often confused with, which is level 2, has high proportion of this feature. So yeah, it's correctly reflecting how model is making decisions, how model is making mistakes in this case. So to recap, we talked about a method that can provide quantitative global explanation, by which I mean explanation that is not just true for this one picture, but lots of pictures in the same class, of using a concept that you chose, the users chose. You can run hypothesis testing based on, what about this crazy concept that I just came up with? How much that is important for this prediction? And I showed that this sort of probing method can help you ensure that your model is reflecting the values that you care, such as fairness, and also ensure that our domain expert knowledge that machine learning model or data may not have is appropriately reflected. With that, I'm happy to answer any questions.
We have time for quite a few questions.
Hi. Thanks for going over all of this. I like the intuitions that you provide, and I typically enjoy looking at these nice intuitive results. I do have one question though, which is, how does prediction accuracy of the model that you're fitting, this linear model that you're fitting in the latent space, how does it affect the interpretation of the results downstream, right? Because
that's an excellent question. Let me see if I can show you some of the other stuff that I didn't think about, that didn't talk about. So it does affect, but it does affect in a specific way. So maybe your question gets into how do we know that this vector is indeed representing the concept? Because if you had a low accuracy, that you should be worried that is this really the reflection of the concept that I'm representing. So here's one way that we test it. It's a one way to test it. You can do it another way. So instead of using accuracy, we test statistical significance based on the class of interest that you want to test. For instance, so we talked about how we can train this linear classifier. We learned this vector, pretty simple. But I said you can select random images as negative examples for your classifier. Now, because it's random images, you can select as many sets as you want. You can learn as many calves as you want. And you can consider this as, then you can calculate the Teacup score for each of those calves. And if you consider these as samples from a distribution, it might look like this. If it does have high correlation, then it would look like this. Then you can compare this with random concept and see if I had a random vector, is this distinguishable or not? If it's not, then you shouldn't be using this concept. If it is, it's a better news. So all the results that I show you are the ones who passed this test. Question?
Hi, thank you for the great talk. So I just have one question. What are some of your hypotheses as to why your algorithm would focus on the image, not the caption for the car, but not so much for the cucumber?
Oh, yeah. So we think that cucumber has just longer word written in the bottom half, so maybe it was more noticeable to the algorithm. So that's one. Cab images had a taxi or cab like English name in the part of the picture, sometimes all over the place. So maybe it thought, well, there's sometimes cab, there's this letter squirrely thing, I don't really know what it is. So those are high hypotheses. We thought it would be like all models the same, but apparently not.
So my question is that how do you handle the uncertainty in the explanations you give? So for example, in the retinopathy case, with the first level, you said that microaneurysms and hemorrhages can be confused, but my experience, because I worked in this area, that they both confuse with the vessel system itself. So if you give an interpretation based on only these two features, it might be misleading, or is it somehow calculated that could be another kind of factor which you don't consider in a hypothesis testing like this?
Oh, I couldn't quite. Are you asking the label uncertainty? Could you repeat the question?
So I'm not sure if maybe I'm not I don't understand everything correctly. So you compare the first level diabetic retinopathy to the fourth level, and one thing you mentioned is that microaneurysms are identified correctly. Or
microaneurysm is the abbreviation for, I actually don't know I only know abbreviation.
So MA.
Okay.
MA and HMA is hemorrhages.
Got it, yeah.
But both of them are easily confused with the vessel system itself, with image processing. So that could be caused by a factor which you didn't consider in the interpretation.
I see. Interesting question. So for to learn that concept, I think that question has to do with how do you know two things. So how do you know the concept vectors do represent the right thing, not HMA, but MA? And also, how are we certain about the labels that we collected? Because maybe there were some other human errors or other errors. To answer your first question, I think that goes back to the first question about statistical testing. So suppose you had a perfect label for these two things. Then the statistical testing will filter out some of the mistakes. However, if you had a label error that you just don't, that inherently had the wrong label when humans gave you the wrong label, then I think bets are off. Garbage in, garbage out. At that point, it will be hard to distinguish. Maybe third question you're asking is, maybe if network has difficulty distinguishing these two things, then what do we do? In that case, that goes back to, I think, the first question. If network can't distinguish these two things, then it will not pass it is likely to not pass the statistical testing, in which case you will not pass the test and you can't get the explanation at all. Thanks.
Thank you. So how much is this approach sensitive to function class choices and how you feature engineer your functions in the first place?
That's a great question. We tested on image-based neural network only for this case, but I'm interested in extending this to language model, neural machine translation, and other things. So it's TBD. But it's this really simple idea. I think the directional derivative has been around for a while, and being able to learn the semantic vector has been around for a while. There's lots of more sophisticated, better things we can probably do with this simple technique.
Right. So, but even within your network, say, how sensitive is it to your choice of parameters and the way you feature engineer?
I see. So the only parameter that I have a choice here is when I learned the CAV, how the regularizer in my linear classifier, it wasn't sensitive. It was not sensitive that much from my just small testing. We did not do extensive testing. However, I have some reasons to believe that we can learn robust semantic directions, because there are lots of other literatures that show you can learn this gender direction to unbiase it, like Tolga's work, but we have not done exhaustive testing. Good question.
Just a continuation of that, which is potentially implicitly you answered the question, but so it seems that at least at the highest level, there are two steps to the method. One is first trying to, after you've got the concept in whatever form you have, you want to find right embedding into vector space and then do the classification. And that gives you the concept vector. And then two is use that to understand from model's perspective, directional derivative. And the second part seems, while you have done your thing right now for a specific model class, but it doesn't seem like that's fundamentally necessary to, I mean, is it, okay, maybe question is it necessary for the model class to be just neural network based or?
Oh, no, not at all. I think you can, we just thought about this. You can do like, while the details are missing, you can maybe take SVM and you have this kernel embedding space. Now you can consider that as some middle layer and do the same analysis. So yeah, I think you can do many things. Oh yeah, that's links to your question. Maybe we can also do RNNs and LSTMs.